In 1774, Captain James Cook charted a small speck in the South Pacific, Sandy Island, just off the coast of New Caledonia. He noted it by dead reckoning, and over a century later, in 1876, a whaling ship called the Velocity reported heavy breakers and sandy islets in nearly the same waters. Maps updated, charts redrawn. Sandy Island was marked reliably on official documents, nautical directories, global databases, even Google Maps. But there was one problem. It didn't exist. You see, in 2012, an Australian research vessel sailed straight through its coordinates and found nothing but deep ocean. No reef, no landmass, just empty, barren sea, as far as the eye can see. So what was it exactly that Cook saw? What did the Velocity report? Was this some kind of sick British joke? Some believe it was a trick of light, others a cartographic error. But one theory floats above the rest: pumice rafts, floating islands made of volcanic stone, so vast and immense they fooled ships' crews for centuries. And as I was spending a late-night rabbit hole online trying to learn more about these pumice rafts, I realized something even more fascinating. These drifting stones might not just account for phantom islands. They might just help partly explain the biodiversity of our entire planet. So what is a pumice raft? Well, when submarine volcanoes erupt explosively, they eject pumice, a type of volcanic rock so light it floats. The result? Enormous rafts of pumice, which drift for months or even years across oceans. In 2012, an underwater eruption from the Havre volcano in the South Pacific launched a pumice raft that spread over 400 square kilometers in a single day. Over the next 3 months, it scattered pieces across an area larger than all of New Zealand, with some chunks moving as fast as 17 kilometers a day. But beyond their incredible size, what makes pumice rafts truly remarkable is what they might represent. These aren't just barren minerals bobbing through the ocean's waters, but potential cradles for life itself. In a 2011 paper, scientists Brasier and colleagues proposed their reasoning for why pumice might have provided one of the earliest habitats for life on Earth. Why? Because pumice has 4 exceptional properties that give it the ideal conditions to support early life. Unmatched surface area. Pumice has the highest surface area to volume ratio of any rock. Its sponge-like structure offers vast reactive surfaces, giving molecules more chances to interact and form complex chains, possibly even life's early building blocks. Natural flotation. Pumice floats at the air-water boundary, where sunlight, gases, and ocean chemistry converge. This intersection creates an ideal environment for key prebiotic reactions to occur while drifting across the sea. Exposure to extremes. As pumice moves, it cycles through wet and dry, hot and cool conditions. Volatile, like the job market. These environmental swings can trigger vital chemical changes, especially those requiring dehydration or UV exposure. Chemical receptivity. Pumice absorbs organic molecules, metals, and phosphates. It also hosts catalytic minerals like zeolites and titanium oxides, materials that can accelerate reactions and support early metabolic processes. This combination made pumice a kind of floating laboratory in Earth's ancient oceans, one that could have nurtured the very first flickers of life. We still see this potential today. In a 2004 study, Bryan and colleagues tracked pumice from a 2001 eruption in Tonga that drifted over 3,500 kilometers to Australia. Those stones carried over 80 marine species, including Pocillopora and Porrid's corals, goose barnacles, algae, worms, sponges, and even small mollusks. Some corals even thrived during this journey, growing skeletons over the 12 months of floating. This ability for marine life to hitch rides across vast distances ties into a fascinating idea proposed by Jell and Martinelli in 1992, what they called the Vortex model of coral reef biogeography. Rather than seeing ocean currents as barriers, this model treats them as swirling conveyor belts, vortices that gather, mix, and redistribute coral larvae across the Pacific. The center of this biological whirlpool lies in the Coral Triangle, near Indonesia and the Philippines, where biodiversity is richest. From there, larvae spiral outwards, carried by eddies and currents to faraway reefs. It helps explain why places like Christmas Island, which is smack bang in the path of these circulating waters, have far more coral diversity than somewhere like Hawaii, which sits isolated on the edge. In this view, the ocean isn't just a challenge to life's spread, it's the very mechanism that enables it. Side note, while I was reading into Jokiel's study, I found one of his papers in which he documented corals colonizing a plastic sandal. Yes, really, several in fact. One floating flip-flop was found with colonies of coral and algae happily hitching a ride. What was more impressive than the study itself was just the sheer amount of dad jokes one person could squeeze into a short, humorous paper. I won't spoil it for those that want to give it a read themselves, but you can find the paper called How Corals Gain Foothold in New Environments, linked below the subscribe button. These floating stones become arcs, mobile ecosystems, drifting across vast oceans. Some reach distant shores, others reseed coral reefs. In 2019, a massive pumice raft formed near Tonga. According to a study done by Tebbit and others in 2021, it carried numerous species of coral larvae, cyanobacteria, macroalgae, and sponges. Some of these organisms even reached the Great Barrier Reef, potentially playing a part in aiding its recovery. It should be noted that, hypothetically, pumice rafts could carry non-native organisms across vast distances, potentially introducing invasive species to new environments. And pumice rafts, on the larger end of the scale, have been observed causing physical damage to coral reefs through abrasion and shading, which can lead to stress and even disease in these coral communities. In some extreme cases, these rafts have even interfered with fish farms and clogged intakes of ships during major drift events. Modern scientific consensus states that pumice rafts are seen not as flukes of geology, but as powerful forces of biology. Over millions of years, they've carried coral polyps, algae, barnacles, even entire miniature ecosystems across vast stretches of ocean. They've helped species spread, connect, and recover. They may have even played a role in the origin of life itself. Of course, in our modern world, they can sometimes cause problems. But when we zoom out over millennia, it becomes clear. Pumice rafts have shaped our planet's biodiversity in subtle but profound ways. To a point, they've even shaped the way we see this world. Which brings us back to Sandy Island. What Captain Cook saw in 1774 may not have been land at all, but one of these ghostly drifting stone fleets, a floating island, here 1 month, gone the next. And yet, during that brief period of time, this ark bobbed past his ship and left its mark, literally, all across the world. Sandy Island may never have really existed in the traditional sense, but pumice rafts, they've been here all along, and in their quiet, drifting way, they may have helped carry more than what we have come to expect. So let us all collectively take a moment for Captain Cook, and laugh at him for his lack of due diligence in not seeing things for what they were. Not islands of the garden variety, but odd vessels carrying scraps for the recipe of life itself. We hope you enjoyed this video just as much as we enjoyed making it. We're just two dudes trying to do what we love. Be sure to give us a like and subscribe for more content on this strange blue planet of ours. Every little bit counts. Until next time, and may your personal islands be full of life and vigor.